Okay. Part 4, Lecture 5. Formalizing the definition of a tensor. Now, you see, tensor is a map. See, that's important. And today is March 6. Okay? Now, first order tensor. First order tensor, okay, is a vector, okay, which you write, for instance, A is a vector. I define this vector as A mu, okay? There is no error here, you see? And you see, if you are working in two-dimensional, mu will be 1 and 2. If you work in three-dimensional, mu will be 1, 2, 3. You see? So this definition of a vector. Okay? Now, consider V the space vector. Then you have here the space vector V. This is the basis, the vector, the basis vector. That's called a mu. Attention now. This is the component. Okay? It's a very, very important the definition. Okay? So A lower index mu is called covariant. Covariant base vectors. This instead of V is A. A superscript is called contravariant component. Observe that both belongs to the space vector V. Now, you define the space vector V star as dual vector space or covector space. You see this? Then I will define A, let's say nu, and the components A nu. See? So A nu is the base of this dual vector. Okay? Then I write here A nu. This is attentional contravariant basis dual basis vector. You see? Now, why dual? Because they belong to the dual vector space. Okay? Now, A nu is covariant component of vector A. Now, Now, you see, attention now. Subscript is covariant. Superscript is contravariant. Doesn't matter if it belongs to the V or V star. Doesn't matter. You see? That's why there's a superscript nu is covariant dual basis vector. This is a lower index, is covariant component. That's of A. You see? This is a vector A. So they belong, I'll put it here. Okay. They belong, right here. They belong to the dual vector space. It's very important. Now, one that's very, very important is this. Attention now. Attention. Vector A is invariant. What means that? Vector A can be represented, okay, using this basis vector, this basis, okay, that's covariant. This will be A mu, A mu. This is the same vector, A nu, A nu. You see, the vector, I can express the vector using any coordinate system. You see? Attention now. You see, we emphasized this in previous videos. You see? That A is invariant. Is invariant. Now, we define, that's a definition, okay? Because I want to, now I want to apply, okay, the concept such that this tensor is a map. That's why I define A nu, comma, A mu is defined as the Kroneck delta nu and mu. Attention here, attention. You see, mu is a lower index. Nu is the upper index. You see, the left-hand side is equal to the right-hand side. Nu and mu are free index. You see, that's important. There are free indices. The same free index on the left-hand side must be the same two, I put here, two free index, two free indices. You see? Now, another point which is very, very important for you to pay attention. Nu is, in this case, is a upper indices. Look on the right hand side. This is nu over here. Nu is a lower index. Look at the right hand side. It's mu there. You see? That's a very important. Also, another important point is this. This here we call the first slot. Okay. By convention, okay, always in the first slot, you set here the dual vector. In this case, dual basis vector. Okay, that's the first slot. And the second one, you just set the basis vector using the lower index. Now, look how interesting. Okay, now I'll show you that the tensor is a map. So I have, in this case, I have V star acting on V must reproduce a scalar. See? Because tensor is a map. Now, how can I write here, over there? So this will be, now first slot, you see? I write A nu, you see? Look. This belongs to the V star. You just look at here in this figure, okay? Comma, A mu, A mu. This is called inner product. When you deal with vectors, okay, these are not necessary vectors, okay? Now, the inner product, when you deal with a vector, this you can substitute inner product by dot product. Okay? This behaves like a dot product. So, this is equal. You see, this I have a mu. Now, the inner product. You see, this over here is just delta.